Hi everyone, it's Mr. Glover here. Just about to get going on our next set of notes. So the topic today is on logarithm laws. So far we've talked about what the logarithm function is, what it looks like graphically. We did a little bit of work using graphing technology. Today we're going to learn the tools to be able to use logarithms algebraically to solve problems. And this will be the starting point of some problem solving. So we're going to start by just doing a few calculations with a graphic or with a calculator, just to see what we get out of logarithms, and we're going to see if we can predict what the rules are. So if you were to input these in your calculator, log 5 plus log 6, you're going to get the number 1.47. Actually, it'll be 1.48. If you do log 11 plus log 9, you'll get 1.996. Log 11 is 1.04. Log 20 is 1.30. Log 30 is 1.48. And log 99 is 1.996. So you might be sitting there wondering why we picked these specific numbers. And if you look at all the numbers across a row, I think you'll see a pattern. First two, or the first one is log 5 plus log 6. Okay, that's 1.48. Log 11 is 1.04. 11 is 5 plus 6. And we see that log 11 is not the same as log 5 plus log 6. So we don't really have a way of adding them, or we don't have confirmation that adding them works. However, log 30, which is 5 times 6, gets us the same number. If we do the same thing with some other numbers, log 11 plus log 9 is 1.996. Log of 20, 20 is 11 plus 9, is not the same. However, log of 99 is, and 99 is 11 times 9. So we definitely haven't proven anything, but I think that this should demonstrate that when you add two logarithms, you can't simply add the input or the argument. You have to multiply those two numbers in your argument. So in other words, log of m plus log of n is log of m times n. Okay, let's see if we can come up with a rule in the other direction. Or actually before that, let's prove why this is. So to do this, log base c of m equals x. We're just going to define it as x. And log base c of n, we're going to define as y. Okay, and there's a couple of things that we're going to get out of this. We're going to get that m equals c to the power x. That's just exponential form of this equation. We're also going to get that n equals c to the power y. Okay, and now I'm going to start with just log of m times n. Okay, log of m times n. And I'm going to see if I can make this equal log of m plus log of n. So what I'm going to do is I'm going to replace m with c to the x and n with c to the y. Okay, so this is going to turn into log of c to the x times c to the y. All right, and now we know the exponent rules for this. We can simply add our exponents. So this equals log of c to the x plus y. And I should probably be more careful. These are log base c's. Now, we had a rule yesterday that if you have a power of your base inside the argument, you can simply cancel. And so log base c of c to the x plus y is simply going to be x plus y. Okay. And now if we go back to what we defined at the top, x is log base c of m. And y is log base c of n. And what we just proved is that log base c of m times n equals log base c of m plus log base c of n. We just went and proved this rule just using some substitutions and some logic. It's maybe not the most rigorous proof, but it'll work. All right, let's try this in the opposite direction. Let's try subtraction. We'll do this fairly quickly. So 0.845 is what you get, log 35 minus log 5. Log of 30 is 1.47 or 1.48. Log of 7 is 0.85 or 845. Log of 48 minus log of 4 is 1.079. Log of 44 is 1.644. And log of 12 is 1.079. So, same thing as we saw before. When you subtract two things, or two logs, you do not get the same answer if you just subtract the arguments. However, 7 is 35 divided by 5. So it appears that if you divide the arguments, it'll work. Let's try another one. Log of 48 minus log of 4. 48 minus 4 is 44. That one doesn't work. 48 divided by 4, however, is 12. And log of 12 is the same as log of 48 minus log of 4. So it looks to me like log of m minus log of n equals log of m divided by n. It's kind of the opposite of what we just did. When we added them, we were multiplying the arguments. And when we're dividing, or when we're subtracting them, we're dividing the arguments. Once again, we can prove this. We can prove this fairly quickly. So we'll use the same rules or same things as before. So log of m over n. If we replace m and n with c to the x and c to the y, log m becomes c to the power x, and n becomes c to the y. Okay. And when you divide exponents, you just subtract them. So this becomes log c to the x minus y. Remember, this is a log base c, which means that the c will cancel out. So will simply become x minus y. And as we define them above, x is log base c of m, and y is log base c of n. So we have gone and proved it now. Log base c of m over n equals log base c of m minus log base c of n. So we now have a way to join logs together. You can only do it if you're adding two logs with the same base or subtracting two logs with the same base, but now we have a way to join them. So in their full glory, the log laws. First two we just proved. Log of m plus log of n equals log of m over n. Or sorry, m times n. What am I doing? This is adding. M times n. Log of m minus log of n is log of m over n. And now there's this last rule. And the last rule is really the important rule. I should probably have named these. The first one I usually call the product rule. Second one, usually the quotient rule. And the last one, the power rule. Okay. Now, this is really why we use logarithms. This is the meat and potatoes, if you will, of this section. And it's this idea that if you have an exponent inside your logarithm, you can remove it and put it out front. So log base c of m to the p equals p times log base c of m. Essentially, what you are able to do here is you're able to take an exponent, remove it from the exponent, and pull it down so that it's now part of the rest of the equation. That's why logs are so powerful. It allows us to solve for things in exponents. There's a bit of work and a bit of algebra involved, but once you get a handle on it, I think you'll find it's not so bad. All right, write each expression in terms of individual logarithms x, y, and z. So now we're going to get to put this all together. The log is base 5, so they're all going to be base 5, okay? Now, what we can do is we can take anything that's being multiplied together and we can just add those logarithms. And when something is being divided, we're going to subtract that logarithm. So in this case, x times y are going to be log of x plus log of y, and then when we divide z, we have to subtract it. So this would equal log base 5 of x plus log base 5 of y minus log base 5 of z. Anything that's on the denominator, we're subtracting because it's being divided. Anything that's in the numerator, we're adding. All right, let's try this again with the next one. This time we've only got one thing in our numerator, so that's going to be the positive term, but we have two things in our denominator, y and root z. So we should have log of x cubed minus log of y minus log of root z. So we can now write this out. There's no label for the base, so we'll call it base 10. Log of x cubed minus log of y minus log root z, okay? And now we've got to do a bit of work. Root z can actually be written as z to the 1/2, so I'm just going to change that. Could have written it in another line, but I don't want to write another line. And now we have two things with exponents. We've got one here above our x, and we have one here above our z. We can pull those exponents out and write them as a coefficient. So this equation boils down to 3 log x minus log y minus 1/2 log z. And that's our answer. Now, if I wanted to solve, well, normally it would be the x would be here, not inside. Then I can rearrange everything by dividing away the logarithm, and I'll be left with my variable. All right, let's try a couple more of these. Log base 6 of 1 over x squared. Now, the x squared is in the denominator, so it's going to be subtracted. This equals log base 6 of 1 minus log base 6 of x squared. We can now take the 2 and move it out front. So this equals log base 6 of 1 minus 2 log base 6 of x. Okay, and now there's a rule here that we've kind of haven't dealt with, and it's that whenever anything's 1 in your argument, you have to remember what the logarithm is doing. The log is saying which power of 6 is 1. Well, 6 to the 0 is 1. Anything to the 0 is 1. So if you have 1 in your argument, that just becomes 0. So this equals 0 minus 2 log base 6 of x, or simply negative 2 log base 6 of x. All right, one more. Log base 7 of the cubic root of x. So now this one, we have to use what we know about powers to move this 3 out of the radical and write it as an exponent. So I'm not even going to get rid of the exponent yet. I'm just going to write log base 7 of x to the 1/3. Now this is part of the argument. This 1/3 represents the cubic root. So I can pull the 1/3 out now. I can write it as 1/3 log base 7 of x. That's my answer. And so we can now do the same thing in the opposite direction. We can now join logs together when we have multiple logs being added or subtracted. We don't have the ability to multiply or divide them nicely. Unfortunately, that would be a real nice rule to have, but the rule is only for when you're subtracting or when you're adding logarithms. And it's a common mistake that people will often make where they try to join things together that are being multiplied or divided. So let's do a couple problems. Use the log laws to simplify and evaluate each expression. So we've got log base 6 of 8 plus log base 6 of 9 minus log base 6 of 2. They all have to be the same base for this to work. And that's really important here. If this was log base 5, you can't do this. But they are all log base 6. So I'm going to write log base 6. That's my log that I'm joining them all into. The ones being added become numerators, and the ones being subtracted become denominators. So this becomes log base 6 of 8 times 9 divided by 2. 8 times 9 because it's log base 6 of 8 plus log base 6 of 9. And then divided by 2 because we're subtracting log base 6 of 2. We can now do a little bit of simplifying. Write this as log base 6 of 36. And wouldn't you know it, 36 is a power of 6. 36 is 6 squared. So this is log base 6 of 6 squared. Cancel out the 6. And our answer is just 2. Okay. Let's try this one. Log base 7 of 7 to the root 7. So now this one looks like something you should be able to put in your calculator, but it's not that simple because we have a base of 7, not a base of 10. What I'm going to do first is I'm going to try and split this log up. Okay, so I'm going to write this as log base 7 of 7 plus log base 7 of root 7. Okay, just because these are being multiplied. And now I'm going to take the 7 in my second term and I'm going to write the square root as its exponent. So this becomes log base 7 of 7 plus log base 7 of 7 to the 1/2. There's a lot of 7s in this line. Moving on, log base 7 of 7 is simply 1. What power of 7 is 7? Well, it's 1. And now this one, I can take my 1/2, or I can cancel my 7, and I will be left with 1/2. 7 plus 1/2 is 2/2 plus 1/2. And my answer will simply be 3/2. All right, one more of these. This one is, this one's quite ugly, but it's doable. You might need a bit of space, so I'm going to zoom in. 2 log base 2 of 12 plus or minus log base 2 of 6 plus 1/3 log base 2 of 27. So first thing we need to do is we need to deal with these brackets, because I know if I forget to do this, I'm going to forget to make both log base 2 of 6 and 1/3 log base 2 of 27 negatives. So let's do that first. This equals 2 log base 2 of 12 minus log base 2 of 6 minus 1/3 log base 2 of 27. Okay, and that's just because this negative sign applies to both terms. Now I'm going to move everything into my exponents. I can't really join them together if there's a coefficient in front. So I'm going to move this 2 up, and I'm going to move this 1/3 up. So this will turn into log base 2 of 12 squared minus log base 2 of 6 minus log base 2 of 27 to the 1/3. I've got a choice now. I can join everything together, or I can try and simplify what's in my brackets. I'm just going to join it all together, but you can simplify it first. So this term is going to be my numerator, so it's all in log base 2. This will be my numerator, 12 squared. This and this will be part of my denominator because they're being subtracted. So divided by 6 times 27 to the 1/3. Okay. Now I can turn what's in my brackets into real numbers. So 12 squared is 144. This is log base 2. 144 over 6 times 3. And that'll just simplify into log base 2 of 8. Eight can be written as a power of 2, so this equals log base 2 of 2 to the power 3. That's 2, 4, 8. And now I can cancel my 2's. My answer is 3. That is a really ugly way of writing 3, but it all simplifies into a nice answer. It will not always. In real life, if you do much physics, you'll find that it doesn't always work into nice answers, and you're going to be stuck with ugly, ugly fractions or decimals, but that's okay. All right, write each expression as a single logarithm in simplest form. State the restrictions on the variable. So we are going to do what we just did, but this time there's variables in our logs. We are going to simplify as much as we can And then we're going to use the fact that variables are in our logarithms to write some restrictions. Okay. So now log base 7 of x squared plus log base 7 of x minus 5 log base 7 of x over 2. Okay. I'm going to simplify this a little bit. So this is going to equal log base 7 of x squared plus log base 7 of x minus 5 over 2 log base 7 of x. Okay. And now I could put all these terms together, but I think what will make it a little easier is if I simply join all of my terms, all of my logs together. There's 3 coefficients here. There is, or sorry, what am I saying? I need to move this up top first. Once I get rid of my coefficient and everything becomes a 1, then I can join my terms together. So this is log base 7 of x squared plus log base 7 of x minus log base 7 of x to the 5 over 2. Now I can join these together. So this is log base 7 of x squared times x divided by x to the 5 halves. We've got a bit of work to do with our exponents. So this equals log base 7 of x to the 2 plus 1 minus 5 over 2. The 2 comes from this term plus 1 because we're multiplying this, and then minus 5 halves because we're subtracting it. So we'll turn into log base 7 of x to the power of, this needs to be written with a denominator of 2, so it'll be 4 over 2 plus 2 over 2 minus 5 over 2. And finally, log base 7 of x to the 1 half. What are our restrictions on our variable? Well, if we go back to the original equation, we had logs in our argument. Because of that, we can't have a 0 in our logarithm. So you're not going to make 0 or negative numbers. So because of that, x has a restriction on it. X must be greater than or equal to 0. And that technically starts up here, but it has to be carried through to the bottom. X must be greater than, or sorry, strictly greater than 0. If there's a 0 in here, then the logarithm is essentially trying to figure out which power of 7 is 0. There's no way to make 7 0 with an exponent. If it's a negative, again, it's also not going to work. So we're stuck with exclusively greater than 0. Moving on, do another one. We've got to join these together. And we can do that in our first step. So they're being subtracted. This will become log base 5 of 2x minus 2 divided by x squared plus 2x minus 3. Okay. Now we have to try and cancel anything out that we can. What that means is I'm going to have to factor my denominator, if possible. This equals log base 5. I'm going to pull a 2 out of the numerator, so 2 and then x minus 1. In my denominator, I need 2 numbers that multiply to minus 3, but add to plus 2. Minus, what am I thinking here? Minus 3 and positive 1 would fit the bill. X plus 3 and x minus 1. And wouldn't you know it, one of these terms cancels. X minus 1 will cancel. So this will simplify into log base 5 of 2 over x plus 3. And can we simplify this anymore? No, that's it. That is as far as we can go. All right, so that should give you a taste of the kinds of questions where you are going to be using algebra to join logs together. Now, don't worry, we'll do lots more of these. What I want to do is I want to focus on some applications of this, okay? This is particularly useful when you've got scales that increase exponentially. So if you've got something like the Richter scale with earthquakes, where a 1 is 10 times as powerful as a 0, or 2 is 10 times as powerful as a 1. Same with pH. pH of 7 versus a pH of 6 has to do with the 10 times more concentration. So it's an exponential scale. So because of that, this is great because we can take our exponents and just remove them. Now, if you're taking chemistry, you might know some other ways of solving these problems that are faster. I'm not saying this is necessarily the only way to do it, but this is the way to do it using logarithms, or a way to do it using logarithms. So the pH scale is used to measure the acidity or alkalinity of a solution. The pH of a solution is defined as pH equals negative log H plus, where H plus is the hydrogen ion concentration in moles per liter. A neutral solution such as pure water has a pH of 7. Solutions with a pH of less than 7 are acidic, and solutions with a pH of greater than 7 are basic or alkaline. The closer the pH is to 0, the more acidic the solution is. A common ingredient in cola drinks is phosphoric acid, the same ingredient found in many rust removers. Cola drink has a pH of 2.5. Milk has a pH of 6.6. How many times as acidic is milk, or as milk is a cola drink? So we've got quite a long-winded question, but really there's only a few pieces of information that are important in here. We've got this fact that pH equals minus log of H plus. Okay, and H plus is the hydrogen ion concentration. And I've got the cola drink has a pH of 2.5, and milk has a pH of 6.6. That's really the important information. When you talk about how acidic something is, what you're talking about is how many H plus ions there are. What's the concentration of hydrogen? The more you have, the more acidic you are. Okay, so I need to take the ratio of H plus in cola and compare it to the ratio of, or to H plus in milk. If I take the ratio of those two numbers, I'll figure out how many times as acidic. It's kind of like if someone was 6 foot tall and someone was 3 feet tall, if you took the ratio of 6 divided by 3, the one person is 2 times as tall as the other. We're just doing that, except we don't have height. Our measure is H plus concentration. So we've got to do a bit of math for cola and milk. In fact, let's space this out a little bit. All right, so let's set up our equation. pH equals minus log concentration H plus. What I can now do is I can plug in my numbers. I know the pH for cola is 2.5, so 2.5 equals minus log H plus. And actually, I'm just going to start calling this HC for H of cola. Okay. Now I can move the minus sign over. Minus 2.5 equals log H cola. And I can write this in exponential form. Exponential form is the base to this power equals the argument. So 10 to the minus 2.5 equals concentration of H cola. So 10 to the minus 22.5 is the molar concentration of hydrogen and ions in cola. All right, let's do the same thing for milk. So pH equals minus log concentration of H plus. Put in our numbers. For milk, it has a pH of 6.6 equals minus log concentration of H. I'm going to call it HM. Put the minus sign to the other side. Minus 6.6 equals log concentration of HM. And write it in exponential form. So 10 to the negative 6.6 equals concentration of hydrogen in milk. So what we've done is we've actually found the hydrogen ion concentration. I could turn these into decimals if I want to, but I'm going to leave them like this because I just want to do one calculation. So if I want to figure out how many times as acidic, that's what I do over here. So the number of times as acidic is based on the ratio of how much hydrogen is in cola divided by how much hydrogen is in milk. So if I go H plus cola divided by H plus milk, then I would be doing 10 to the minus 2.5 divided by 10 to the minus 6.6. And I would find that this, well, I could do this by hand. I'm just going to punch this into a calculator. I would find that this is 63,096 times as acidic. And so that sort of thing is only possible because this is an exponential scale. Every one in my exponent increases by a factor of 10. So we're going from like 10 times to 100 times to 1,000 times to 10,000 times as strong. And that's the difference between a 2 and a 6 here. We're going to do the same kind of thing in a different order. So the apple, or an apple, is 5 times as acidic as a pear. A pear has a pH of 3.8. What is the pH of an apple? Okay, so we're going to start with this equation right here. We know that which one's more acidic? The apple is more acidic. So I know that the hydrogen ion concentration of an apple divided by the hydrogen ion concentration of a pear is equal to 5, because it's 5 times as acidic. Okay, now I know the hydrogen ion concentration of an apple is going to be 10 to some power. So I'm just going to call it 10 to the minus x so far. And I know that the pH of a pear is 3.8. So I can call that hydrogen ion concentration 10 to the minus 3.8 equals 5. Okay. At this point, we have a couple of ways we could do this. We could start by joining these exponents together, but that might not be the easiest way of doing it. What I'm going to do is multiply 5 times 10 to the minus 3.8. So I'm just multiplying my denominator. 10 to the minus x equals 5 times 10 to the minus 3.8. And now I can take the log of both sides. This is something we haven't done before. Take log of both sides. If you want, you can turn this into a decimal, but I'm going to leave it as is. So log of 10 to the minus x equals log of 5 times 10 to the minus 3.8. I can move the x out of my exponent. Minus x log base 10, or log of 10, equals log of 5 times 10 to the minus 3.8. And if I want to solve for x, I just have to divide by minus 1 and log 10. So x equals log of 5 times 10 to the minus 3.8 over negative log 10. And what I'm going to get is that x equals 3.1. So that would be the pH of a pear. Or sorry, an apple. So this is a bit of a roundabout way of doing it. If you're in a chemistry class and you've learned other ways of doing this, do it that way if you find it easier. But this is just one method of solving these kinds of problems. So I think that's where I'm going to end the notes today. We've gone through quite a lot, and it's going to take a little bit of time for this to all sink in. These new rules are going to be something that we use for the next several classes. We will do some transformations of log functions, but otherwise the majority of what we're doing is working with these types of questions by hand to solve problems involving logs and exponents. By the way, we now have the ability to solve equations that we were doing at the start of this unit, but we can solve them with logs instead of by rewriting our base. Anyways, I'm going to end the video. Have yourselves a great weekend. I will see you all on Monday. And yeah, if you have any questions, just feel free to shoot me an email. Bye for now.